Okay, so what we're looking at now is some calculations and some definitions that go along with the kind of problems that we were just doing. These kinds of problems in general are known as stoichiometry problems. And stoichiometry is really the math that goes along with calculating chemical quantities. And the way I like to introduce it is something called the bicycle factory. Okay, so imagine that you have, or I have, a bicycle factory. My family actually had a bicycle store not that long ago. But let's say I have a bicycle factory, and in my factory I have 10 frames and 14 wheels. And when you put bikes together, you probably know how this goes. You have frames, and you have wheels, and you can make bicycles. Okay, so pretty crude, but you can put bicycle wheels on here, and then you have your bicycle. Okay, so that's my reaction. Is that balanced? And the answer is no, because if I only used one wheel, it would be a unicycle, right? So I have to put a 2 here. So that's how my bicycle factory puts the bicycles together. I know it's kind of crude, but it's good enough. So how many bikes can you make for 14 frames, or for 10 frames and 14 wheels, right? Think about that. You have 10 frames, and you have 14 wheels. How many bikes can you make? If you said 7, you're correct, okay? Why can you only make 7? Well, many of you did that just by saying to yourself, it's 2 wheels for every bicycle, so I could only make 7, right? What you automatically did there was a mole type conversion, a stoichiometry problem. So the problem sets up like this. I want to make bicycles, because remember, write down what you're looking for. And I've been given 14 wheels. And it's 2 wheels, I'll just call them WHs, for every one bicycle. The wheels will cancel, and that gives me 7 bicycles. But there's actually another part to this calculation that you did in your head without even thinking. Okay, and the calculation was this. You had 10 frames. 10 frames of 10 bikes, right? And you knew you couldn't make 10 because you ran out of wheels. That's the other calculation you did in your head. You said bicycles. It's going to be 10 frames, and then it's going to be 2 or 1 frame for 1 bicycle. And then you came up with this number, 10. And you discarded it in your head right away because you knew you couldn't get past 7. Because what happens when you get to 7? All right, think about that. What happens when you get to 7 bicycles? You run out of wheels. You can't go past that. So here are some terms and definitions related to this calculation and as they apply to chemistry. The wheels are a limiting supply for making the bicycles. So in chemistry, we would call it a reactant. It's one of the things I need to make the products, right? So the bicycle is the product. So we would call the wheels the limiting reactant. It limits how many bicycles I can make. The frames, so this is the wheels, right? The frames are known as the excess reactant. Now, there's a couple other terms here. One term is theoretical yield. How much could you make from these supplies, right? So the theoretical yield is this number. And it is always the smaller of the two. Because when you make this theoretical yield of material, you've used up the limiting reactant. So how much limiting reactant is left? None. Now, if you wanted to, you could calculate how much of the excess reactant remained as well. Because now that you know you can make 7 bicycles, you know that you have 7 frames left, and you just subtract the 7 from what you started from, and that'll tell you you have 3 bicycle frames. And this is how you would run a business that runs on a tight supply chain, for example, right? You don't carry around. This is kind of the problem of the grocery store model that we have in lots of businesses we have in the United States. They run on a tight supply chain, and when any part of that supply chain breaks down, you can't make anymore. So a lot of businesses operate on this principle. It was originally come up with by the Toyota company back in, I think, the 60s or 70s, when they looked at American companies to try to figure out how to be competitive. And so, but small businesses have to do this. And so if you have 3 frames left over as you're making these bikes, you're thinking to yourself, I better order some wheels. How many more wheels do I need? And you'll come up with the number 6 if you think about it. And then you order things just so that you always have enough to keep going and don't have to store or pay for any of the excess inventory. So chemical reactions are operated in much the same way. We have a limiting reactant. It limits how much we're going to make, but then we also have an excess reactant, and if we need to, we can figure out how much of the limiting reactant needs to be added up to use all of that up, okay? So sort of to summarize all this, I'd actually forgotten I had these slides here, but sort of to summarize all this, right? First thing you have to do when you do one of these problems is you have to have a balanced equation. And this particular problem, we had the frames, we had the wheels, and we had the bicycles as the product. Oops, broke my bicycle. We'll talk about that in a second. Right? And then I got a theoretical yield, right? And the theoretical yield was based on the limiting reactant. And when it's based on the limiting reactant, what we're saying is that the limiting reactant ran out. And when it runs out, there's none left. And there's none left. And that's why the reaction stops. In this particular instance, my limiting reactants was the wheels. That's what ran out. And the excess reactant was the frames that I had for my bicycles. And then we talked about, how you could calculate the excess reactant that was left simply by using the number of bicycles that was produced to calculate how many of the frames actually were used. And I could subtract that from what I started with to figure out how much was remaining. There's one other concept in this limiting reactant theoretical yield idea. It's called the percent yield. So the actual yield is what you measure, okay? Now, if you were only able to make 6 bikes, your actual yield would be the 6 bikes. Maybe I mangled one of the frames, maybe the frames were defective, and for some reason I couldn't make a bicycle out of it. And this happens, right, in businesses and everything. Well, what's the percent of product that I make? Well, the percent of product that I make is there's percent yield is percent, and I often do this. Percent theoretical yield is what we're really talking about. The theoretical yield is how much I could have made. In this instance, it's 7. The actual yield is 6, okay? And then I multiply by 100%. So this is theoretical yield. Let me write it out. And this is the actual yield. You either have to be told what the actual yield is, or sometimes a question will ask you what is the actual yield, in which case you need to know the theoretical yield and the percent theoretical yield, and then you could calculate the actual yield by rearranging the equation, for example. Okay, so let's apply these ideas to an actual chemical problem. So I'm going to talk you through it a little bit and have you figure out different parts. And at each point, I'll pause, and then we'll talk about what the answer ends up being. So you have this magnesium nitride reaction, which we balanced earlier in the lecture series. So you have 3 moles of Mg3N2, magnesium nitride, and it reacts with 15 moles of water. How many moles of magnesium hydroxide can be formed? Now think about it like this in the general term. You have wheels and frames again, except it's not 2 to 1, right? It's 6 to 1. 6 waters being like 6 wheels. So you're maybe making an all-terrain vehicle of some sort, right? And then from that, we're trying to figure out how much magnesium hydroxide could be produced. Those are my bicycles, right? So again, I'm going to have to do 2 calculations, because in these limiting reactant problems, you're given moles of 2 different substances. And the first problem we did like this, we just were given moles of one kind of substance and asked to calculate how much you could make. That was also a theoretical yield problem. But since we're given moles of 2 reactants, just like wheels and frames, you have to figure out how much could you make from each one, and then compare the 2. Okay, so let's go ahead and do this. I'm going to say I want moles of moles of MgOH2, and this is going to be from Mg3N2. Okay, so go ahead and do that calculation, and when you're done, this answer will be on the screen. Okay, so there's the answer. I was given 3 moles of magnesium nitride. I pulled my mole ratio. It's 1 magnesium nitride for every 3 magnesium hydroxides. So that's where I get this mole ratio from. And then I canceled out my units of magnesium nitride to leave with moles of magnesium hydroxide, and that gives me 9 moles. So with 3 moles of magnesium nitride, I get 9 moles of magnesium hydroxide. The next thing you want to do is you want to calculate the moles of magnesium hydroxide that you can produce from water. Now, for every reactant, you have to do this. So if there were 3 reactants, we'd have another one after this. Go ahead and do that calculation, and then we'll talk about the results. Okay, so there is the answer. And I can get 7.5 moles, and I got that by looking for the moles of water that were given. So that's where I started the calculation over here. All right, and then I looked for my mole ratio. So there's 3 magnesium hydroxides for every 6 moles of water. So that's what I get here. So it's basically a factor of a half. So I end up with 7.5 moles of magnesium hydroxide. So now I'm looking at these 2 numbers, right? I just did all these calculations. When you do this, pause for a second and think about what the answers mean. When you get to 7.5 moles, the reaction stops. And the reason it stops is you used up all the water in the reaction. And so you have 7.5 moles of magnesium hydroxide produced. You have some excess magnesium nitride. But the theoretical yield for this reaction is 7.5 moles of magnesium hydroxide. Okay, so let's summarize what we know about mole-to-mole conversions. The problem-solving pathway is always moles of A to moles of B, and you need a mole ratio from a balanced chemical reaction. If you calculate from the limiting reactant, the number you get is the theoretical yield. It's the most you can make given the amount of reactant you're given. and the limiting reactant runs out, so none of it's left. That's why the reaction stops. And in the cases where you're given 2 reactants or more, you have to calculate the product produced by both reactants, and the smaller quantity is always the theoretical yield. And the reactant that gave you that number is the limiting reactant, and the other one will be your excess. Percent theoretical yield is what you get when you know an actual yield. So if you knew how much you made, you just take the actual, you divide it by the theoretical, and you multiply it by 100. That's why it's called the percent of the theoretical yield, or percent theoretical yield. Next, what we'll do is start looking at how we use these kind of calculations in the lab, because we can't measure moles usually very easily, and we always are measuring grams. And so we'll look how we start incorporating grams in these calculations.